This lesson covers the physical basis of NMR. I would like to preface by saying that it is actually not necessary to understand anything that's in this lesson in terms of the physics behind NMR in order to be able to interpret spectra, which is the real task that organic chemists have to be able to carry out. However, I would not be doing my duty as a teacher of this material if I completely ignored the physical basis. So hopefully you'll be able to get something out of this lesson, at least for your own edification. And the way I'm going to go through this process is to go through the three words, nuclear, magnetic, and resonance, and explain to you what each of these words means in the context of an NMR experiment. So we will begin with the word nuclear. Well, obviously nuclear has to do with a nucleus. But what is the property of the nucleus that we care about? The property is called nuclear spin. So many nuclei have a spin, just like electrons have a spin. And the way to know if a particular nucleus is going to have a spin is to look at its atomic number and its mass number. So if either of those numbers is odd, the nucleus will have a spin. If both numbers are even, there will not be a nuclear spin. So of the nuclei common to organic chemistry, carbon-12 and oxygen-16 have no spin, because carbon, of course, has atomic number 6, and oxygen has atomic number 8. So both of those numbers, all of those numbers are even. However, hydrogen, having both an odd atomic number and an odd mass number, has spin 1/2, which makes it very easy to observe. So there are other important spin 1/2 nuclei, such as carbon-13, fluorine-19, and phosphorus-31. All of them are used by practicing chemists in their analysis of the structures of molecules. Carbon-13 is actually particularly useful because in addition to organic molecules having a lot of hydrogen, organic molecules also have a lot of carbon. However, carbon-13 is a rare isotope of carbon, so in order to be able to observe carbon-13, you have to change the experimental parameters sufficiently that the details of carbon-13 NMR are actually different from the details of proton NMR. As a result, in this introduction to NMR spectroscopy, we're not going to cover carbon-13 and we're just going to focus on protons. Okay, magnetic. Well, when you put nuclei into a magnetic field, they will either line up with their spins parallel to the direction of the magnetic field or opposite to the direction of the magnetic field. So in this figure here, in the absence of the magnetic field, the nuclear spins the spin vectors can be pointing in any direction that you want. But when you add a magnetic field going from top to bottom in the diagram, the nuclei that line up parallel to the field, we call them spin up, or some people refer to this as the alpha spin state. I like spin up better than the alpha spin state. You know, I'm just one of those kinds of guys who doesn't like to use Greek letters any more than he has to, and there are enough Greek letters that we have to deal with in this unit anyway. So parallel to the field is spin up, opposite the magnetic field is spin down. And you can see here that there are a number, just for the sake of argument, they gave 7 spins here, and you can see that 4 of them are spin up and 3 of them are spin down. So if we're talking about a magnetic field, one important question is how strong of a magnetic field are we talking about? And that's actually a really important point. The magnetic field for doing NMR is a very strong magnetic field. So typically a magnetic field that is used is one that is 9.4 Teslas in strength. Now, you can go be a physicist and define Teslas in terms of fundamental physical constants. I don't want to do that. What I will tell you is 1 Tesla is 10,000 Gauss. Well, Gauss is also a unit of magnetic field strength that's defined in terms of physical constants. That's also not particularly useful to me. What is useful to me is the fact that a typical refrigerator magnet has a magnetic field strength of about 50 Gauss. So now I could say that an NMR magnet is about 2,000 times stronger than a refrigerator magnet is. There are a lot of technical implications of this point that are not really important for understanding how to interpret the spectra. But if you take a look at the NMR spectrometer, you will see that the magnet is actually quite large. And the reason for that is in order to get such a strong magnetic field, you can't even make a regular electromagnet that's that strong. You need a superconducting coil. So superconductors are substances that have 0 electrical resistance. Now, the downside of superconductors is that there are no materials that we know of that are superconductors at room temperature. In order to make materials superconduct, you have to cool them to low temperatures. And the magnetic coil inside a modern NMR spectrometer is actually cooled down to 4 degrees Kelvin. And so that's negative 269 degrees Celsius. And the way we get down to 4 degrees Kelvin is to immerse them in a bath of liquid helium. Okay, so liquid helium is really, really cold, and what keeps the liquid helium cold for a long time is you have them immersed in a bath of, the liquid helium is immersed in a bath of liquid nitrogen, which is at a temperature of 77 Kelvin, but liquid nitrogen is much, much cheaper and readily available than liquid helium is. Anyway, I'm getting off on a tangent here. Suffice it to say that you need a strong magnetic field to be able to do NMR. Okay, the last of the 3 terms we have to consider is that of resonance, and this is the most complicated one. So first of all, this use of the word resonance is completely unrelated to resonance structures. So get that out of your head. It is closer to the physics definition of resonance, in which you have, a sound wave resonating in a particular cavity, for example, but it's not even exactly that. It's only using resonance in the sense of something moving back and forth. Okay, so what is the something that moves back and forth? Well, there is an energy difference between the 2 spin states in the presence of a magnetic field. Without a magnetic field, spin states are undefined completely. There's an energy difference between the 2 spin states, with the spin up state slightly lower in energy than the spin down state. Okay, so that's indicated here on this diagram. What the diagram is also indicating to you is that the energy difference depends on the field strength. At 0 field, there's no energy difference. NMR used to be run, so 40, 50 years ago, at magnetic field strengths of 1.41 Teslas. That's a magnetic field that you can still get with a really strong electromagnet. So you have an energy gap at 1.41 Teslas, and if you make a field stronger to get up to 7 Teslas, that was kind of the state of the art 20 to 30 years ago, then you have a greater energy difference than you do at 1.41. At 9.4 Teslas, you have an even greater energy difference than you do at 7 Teslas. So what happens is, you notice that any spectroscopy experiment involves taking something that's in a quote-unquote ground state, treating it with energy, and bringing it into the excited state, right? So we could think of the spin up state as being the ground state and the spin down state as being the excited state. So upon absorption of electromagnetic radiation of the proper frequency, a nucleus can flip its spin from the lower energy spin up state to the higher energy spin down state. This spin flip, the going back and forth between spin up and spin down, is where the term resonance comes from. Now, only radiation of exactly the right frequency will cause a spin flip, which we also refer to as satisfying the resonance condition. So this is unlike a UV vis spectrum, which you may be familiar with from a previous course, where there is plenty of absorbance at frequencies slightly higher and slightly lower than the absorbance maximum. A typical peak in a UV vis spectrum is 50 nanometers wide or something like that. With NMR, you got to be right on. That gives rise to much narrower peaks. But you need the peaks to be that narrow to get the chemical information that you need out of the experiment. So the fundamental equation of NMR, which I do not expect you to memorize or even necessarily be able to use to solve problems, so I'm just going to still put it up there, is that the frequency, nu, is equal to 4.26 times 10 to the 7th times the magnetic field strength, B. Now this number, the 4.26 times 10 to the negative 7th, is the number for protons, for hydrogen nuclei. It is a different number for different nuclei, but since we're going to focus on hydrogens, we're just going to use this one. So nu is the frequency of radiation in units of hertz, and B is the magnetic field strength in units of teslas. So if you plug in 9.4 teslas for V and solve for nu, you will get 4.00 times 10 to the 8th hertz, which, to make that sound a little nicer, we will refer to it as 400 megahertz. And this frequency is in the radio wave region of the electromagnetic spectrum. And if you think about radios and you think about the FM dial, that ranges between 88 and 108 megahertz. So this energy difference is just that slightly higher energy than the energy that FM radio is broadcasted in. This energy difference is actually quite small in the grand scheme of things. If you think back to the diagram of the electromagnetic spectrum, radio waves are the lowest energy form of electromagnetic radiation that we reasonably consider. So because this energy difference is so small, there is actually only a slight excess of nuclei that are spin up. That slight excess, we're talking about 10 nuclei out of every million. Again, this is in contrast to electronic spectroscopy, where molecules exist almost exclusively in the ground state, and only for a very short time do a small number of molecules get excited to the excited electronic state. So most nuclei are not actually changing during an NMR experiment. And all the data that we get comes from the relatively small number of nuclei that actually do flip spins when you put them in a magnetic field and expose them to RF radiation. So that's the basic physics of the phenomenon known as nuclear magnetic resonance. What is not clear yet is how this is helpful for deducing the structure of organic molecules. So we will begin to probe that concept in the next lesson.